So the chapter is divided into five subchapter or five sections: quantum state, observable, measuring dynamic, and assembling quantum system. Those are all essential concepts to actually understand and apply quantum computing. So the first one is the quantum system, quantum state. So the basic idea of quantum state really starts from the particle and wave concept. So most of the things when we look at the world, there will be a particle, there are waves, but there are many things are both particle and waves. The wave will be like we throw a stone in a pond, and then we see the wave will spread out on the surface of water. So that clearly is a wave, and that the stone can be considered a particle. But there are other things like a light. So if we shine light on the double slit experiment, if we have a light, and then the light actually form a wave, goes through the double slit, and then each slit become a wave afterwards. When we observe the intensity after the double slit, actually it will be, it's not proportional. Well, it's supposed to be sorry. So the intensity is corresponding, that's probably the correspond to that slit, is correspond to this slit. So light is both, this is the example, light is a wave, but light is also a particle because of the photoelectron experiment. Photoelectric effect, which a photon can be converted into energy. And so that would be, so light is also a particle called photon. Now, and this is basically one of the basic concept which leads to the quantum system. And the book then decide, say, we're going to start with the minimal quantum system. The book, so this is what they call the basic. A basic quantum system we were focusing on. So what this basic system is, a particle in discrete positions on a line, and it's also a single particle spin system. system. So, this basically explained by a diagram. So x0, x1, xi, all the way to. So basically, there is a line here. With a line here, and there's a discrete state that the particle can be in. So now, the way to describe this system, we can use the vector to describe this. So if it's x0, if the system is x0, we can call it what? Is the particle in x0, because the particle can in discrete state. If particle is in 0, it will be 1, 0, 0, 0. Right? And that's the that will be this state. Oh, by the way, yeah, we already started to use this. So this is something we call it cat notation. You can Google, try to find out why it's called cat. That's called a cat notation. And we'll apparently use this a lot if you want to do quantum computing. So that's basically the state, describe a state. And if it's in x2, if it's in actually x1, right, it will be 0, 1. But this is just each particle. If we write the whole thing, we can call it, if we write the whole thing, generalize this, will be a psi cat, which is equal to the complex number C0 versus cat X0, and then followed by another complex number, followed by X1, followed by Cn-1 complex number versus the n-1 cat state. So, and those are these complex numbers. Those are called complex amplitude. Sorry. Oh, light one off. Apparently, if I'm the only one in the building, I could walk around. This is interesting. Yeah, so if I apparently if I'm not walking around, the light went off. I guess when there are more people, someone always moving. But this is kind of odd. Okay. So that the amplitude yes. So now it turns out those amplitude, what this function is trying to describe, a quantum system is basically called, say, this particle can be in n state, x0, x1, x2. And this will be something we call, what is the system? Can someone put in the chat window? What is this? And so in this psi function I'm writing on, and the system, the particle can be in x0, x1, xn minus 1, basically n different state. And this is called what?
Is it superposition?
Excellent. Yeah, this is basically superposition. This is basically superposition. So superposition actually is not something really mystic or magic. So apparently, like on the surface of water, if we throw two stones, and then we will see two waves superposition to each other. Right? So that's, so if one wave, another wave, then you will see two superposition there. So I lost my Apple Pen. Okay. Now, here's the, but what does this function tell us? Is also tell us the probability we will observe the particle at which state. And that probability is actually by taking the square of that amplitude divided by the total vectors sum of that square modulus. So the probability, oops, that's not it. The probability of observe the system at pxi is equal to complex number modulus squared divided by the entire matrix modulus. So that will be entire matrix modulus is basically sum of everything. Right. So basically it's add up everything. So this is clearly something less or equal than 1. So this is actually a probability we have better intuition with. So and if we observe the particle at a particular state, and we often call that the system is collapsed or observed at that particular state. So okay, so in fact, I think I have some Python example. Let me see. Oh, we have a, this is interesting. It looks like I cannot log into my GitHub account. Okay, this is new. This never happened before. Oh.
I think they started, excuse me, I think they started implementing two-factor authentication on GitHub accounts.
Oh. Okay, this is a bit annoying. Okay, I use a different browser login. This is whatever security certainly has not working well. I can log in using a different browser. Okay. Okay. Let me put into the chat window. Is it equivalent to a Fourier series? Not really. Fourier series basically I'm going to minus that it is not, because a quantum state Fourier series is actually the real one. I guess you could have a complex series Fourier series. A Fourier series minus n is basically break a complex a wave into additive one. A superposition is not that case in the sense it has to be, when you observe, it has to be one of them. So Fourier series, you can actually indeed have multiple wave out there. So it's not superposition. I don't think Fourier position is considered a superposition in that case. So in the case, you can in theory indeed have two combination of wave had a Fourier to another wave. That actually is real, but superposition really means when you observe, you only observe one state. So my understanding is not the same, although we could elaborate on that after class. So I put that, let me see whether I can open up share my, so the code I wrote, let me put that in chat window. Yeah, I wrote a chapter for some simple Python code. Show the example. So open Colab, does it work? Yes, it works. Okay, so the first one is just to show how to calculate the probability with the superimposed quantum superposition with a combination of the complex amplitude plus the state. So we have a very simple complex vector. Is that from the book? Not exactly, but it's just a different vector. It's not a book example, but the same principle will work. So first calculate the entire vectors modulus. The entire vector modulus is what, 5.47. And then we calculate each state, the modulus, called modulus by element. And then for each, I didn't print out, actually did print out, but for each state, we print out its modulus and the probability, which basically the modulus divided by entire vector's norm. And then we confirm the entire probability should sum up to 1. So let's change that into the book example. The book example is what? Let's see. The book example minus 3 minus 1i, and then minus 2i, followed by I, followed by 2, which is 0j. What can you say? Okay, this is the book example. It's not exactly 1.0, but close enough. So this is the, let me write it down. Example 4.1.1, sorry.
If the complex numbers were all equivalent, would you expect even distribution?
You should, yeah.
Okay.
Yeah, you can try that, yeah. So this is the book example. Maybe I should add example 4.111, yeah. So, okay. For x2, x2 basically is a third. What's the probability? .05, yeah, 0.05. That's 52624, 526. This is different from the book. Up to a few digits. Upon the book seems to round up the number. 4.3589. 4.3. Yeah, the book round up the number. I should give a different value. Okay. So the book actually then give you a few more exercise. I guess you can actually write a Python code just to see whether those are correct or not. Yeah. Now this is a good exercise. Exercise. Multiply well, it doesn't copy paste. Okay, I have to type it in. Multiply by a complex number. C, check that it will not alter the probability. Yeah. Oops, this didn't write. Oh, I copy paste the wrong place. Okay. This is, yeah. Yeah, I don't know how to write a mic down the cat on sign symbol on the side. Oh, I'm going to just leave it this. So
I think you can put dollar signs on both sides.
Really? Okay, let's try that. Oh, thank you. It worked. Okay. And there must be a more aesthetic cat symbol. This is just greater than sign. Anyhow, I'm going to stay with this. So how do we do this? Multiply a state vector by a complex number and check it does not alter the probability.
I think NumPy gives you vector scalar multiplication.
Okay.
So you have the vector already somewhere there, your complex vector. So I think you can just make a new vector and assign it the value of complex vector times some complex number. So in your code cell, we can go right above.
So I'm going to copy paste this part
Yeah, why not?
to the bottom. Now,
so you can just write on your first line, you can just multiply a complex number by your NP array. Okay.
I just put the one value.
You already have your complex vector. Just use that.
No, you have to put a one.
Okay.
Let's say 1 plus 2j. Okay. Okay, I think we are overkilling it. Don't use array, just say the number directly. And then it will be easier. Will that just work?
Yes. Should work.
Yeah.
So just print that afterwards and you can see for sure.
No, that didn't, there's an error there.
What's the error?
C0 is not defined. Oh, I put it in capital. Okay.
Oh. Well, nearly the same.
That is interesting. It's actually 1 point. Okay, that is funny though. But the probability does look like similar. This numerically it is close. Yeah. 5263. Yeah. Although the total probability actually now slightly greater than 1, that is a bit funny though.
Effectively equivalent.
Yeah, this is interesting. Yeah. Okay, it's good exercise. So, in theory, basically, it doesn't change. So, in a way, and then we just normalize everything. just use a normalized one will represent the all other values. So in a way, it's actually really simplified the quantum computing in a way. So in a way, let me look at that.
I suspect if we normalize this, that we would actually get a real one for both of, well, obviously for both of them, but yeah. And instead of 0.9999, I think we'd get one.
Good point. We could try. I mean, see whether we normalize it. Yeah, let's try whether. So the question, good question, yeah. If we normalize, will the numerical improve numerical position? This is actually quite a practical question. So good question. Let's try this. It probably depends on implementation, but let's try to normalize this.
Sort of making you suspect those NumPy guys, right?
You have to update the modulus vectors again too. Will that work? Sorry, auto order. Okay, so we'll now. Wow, it is 1.0.
Yeah, this is very cool.
Well, good question. Yeah, it indeed improved the numerical precision. Okay. Very good. That seems to be a very simple trick to improve numerical precision. Also, another reason why we use normalized one.
Yeah.
Very good. Yeah. Very good. Yeah. This is cool.
Just for grins, as long as we're playing around, can we make all 4 elements of the original vector equivalent and make sure that the probability distribution comes out even?
Sure.
Yay. Okay.
Yeah, very good. Although it's not a one anymore.
No.
That's interesting.
Yeah. Well, again, if we normalize that one, I bet we get one, I'm pretty
We
sure.
also normalize this one. This is.
Oh yeah, we did.
Oh,
That's
this
interesting.
actually, it doesn't look like normalization, not necessarily improve your position.
Yeah.
Well, that may just be floating point error.
Yeah, it actually, you can even see it doesn't even sound up to be the same.
Yeah.
Yeah.
I-
Yeah,
Oh.
because still good exercise. Yeah. So,
Yeah.
mhm.
Now I'm worried.
Yeah, but you have to see what's the number of that 1, 2, 3, 4, 5,
Yeah.
7,
Yeah,
8,
what is that?
9, 10, 11, 12, 13, 14, 15, 16, 17.
True. Yeah.
He probably doesn't care.
Yeah. Yeah.
Okay.
What do you expect from a CPU, right? Yeah.
Right. Okay. But it actually doesn't sound up to be the same anymore. Still good exercise. Yeah. So okay, let me see. And this is the yeah. Now it goes to the next part. Hold on. I'm jumping ahead. So I covered the normalization. Oh, now there's the spinning part. The concept of spinning is basically two state, up and down. I guess I still, just to be consistent, still write it here. So, so I covered the normalization, and the next concept the book emphasizes is the spin. So the spin, the book basically use the example of let's see, a very old experiment that electrons in a magnetic field can spin up and down. It's actually a 1922 experiment. I guess that's also when the quantum physics start to develop. So yeah, a quantum system can spin up and down for two states. In that case, we will have to write down the quantum system as, sorry, number. Actually, this seems to be a really challenging for handwriting. Yeah, up state and down state. So, and that will be probably one of the simplest system. So instead of n state, it's not just the two state. And the next concept is the so-called, I think I'm going to start with a new page. To emphasize those, the so-called transitional amplitude. Transition amplitude. So we will have a two state, one is the beginning state, one is the end state, and we will calculate the chance that let's see, the so-called bracket inner product. I'm trying to make sure I'm not misrepresenting what this means. So in this case, there'll be some really strange symbols here, but once we are used to it, it's just a way to write to represent the transition. So if we have a one state phi psi and another state psi prime, this is start, this is end, this is start state, this is end state, oops, end state. Okay. So the transition amplitude from the start to the end state is represented by the so-called bracket bracket pair. Bracket or inner product. So this, yeah, apparently, if you think about the complex line inner product, is also the same symbol. So it just come back. I guess the symbol wise is also a self-consistent. So, and then we basically have the two calculated inner product of the two state. And the first one had to be conjugated transpose. So that would be and the next one is the same. C0, C1, C2. So, so this apparently describe the from the starting state and ending state, how the amplitude go from the first one to the second one. This is, and the book basically then show the starting state amplitude amplitude modulus square is basically the probability. I think next time I won't go to a classroom myself. I keep waving my arm to keep the light on. Sorry. I think I tried to write okay, 4.6. This should be my next Python example. Yes. So the book's next example, let's write it down. This is kind of abstractive, so we use the example. In fact, it's just also spin example up and down, just two state, two position. So we have a psi. We have another one called phi or phi. Okay, so we need to calculate we need to calculate the inner product of the psi is the start, phi is the end, so that's the inner product. Let me show my Python code again. Well, I guess we could do it manually as well. So
Can't we ignore the coefficients because they're constant?
it's good. I think it will affect the result.
Maybe you're right. It's hard to remember that stuff. Yeah.
So we first found out so from the cat, we found out that the bra phi. Minus is that correct? That's correct. Yeah. So, but I also had a Python code to show this. Yeah, so this is what I wrote a Python code to do the example for 4.0. We have a psi is that psi one I, is that correct? That's correct. With the coefficient on the side. Where the phi that's also correct. That's phi and psi. Then we compute the bra of phi. We say this is a conjugate. Then compute the inner product of phi and psi. Oh, did I say conjugate or transpose? No, it's just conjugate, sorry. Then we have the transitional amplitude of the dot product of bra and psi. The result is minus I. In Python, it's minus 1j. Okay, so. Yeah. The book actually gave you another exercise. I guess the book gave you ask you to do another exercise. For 110. That one. I'm going to let you work on that after class. So let me look at my notes. Transitional. Actually, that seems to be the important part of the first part, basic quantum information, basic quantum state. So. Okay, and then the next chapter, next section is observables. This is built on the first part. Let me go back to my The next part of the book is observable, section 2. Apparently, there are some given postulate or theorem, whatever, and we basically take it as it is. So the quantum state, if it's observable for us, it has to be a so-called Hermitian operator. So for us, physical observables will lead to a Hermitian operator. So to me, this just taken as it is. I wasn't trained to be a theoretical quantum physicist, so this is just given. We accept. I will just accept. Let's accept this is true. So the second. The eigenvalue, let's call that omega. The eigenvalue in omega are the only observables, only possible observables. And the eigenvector of omega actually is the basis vector, is a basis vector of the state space. So to me, I would just accept this is true. There are very smart people in theoretical quantum physics has found probably found out those rules, and we just accept it. So now with this, we actually we can go back to see what is a Hermitian operator. The Hermitian operator definition is let's see. Can someone put in the chat window? What is a Hermitian operator?
It's in the chat.
Yeah. It's a Hermitian. Okay. The Hermitian matrix is basically is equal to its conjugated transpose of itself. So that's the definition. Okay. I apologize. I didn't realize I probably wasn't sharing this. So according to the book, there are two very important principles. We just take it as it is. So for a quantum state, the physical observable, which I understand basically what we can see, so is done by the Hermitian operator, basically a Hermitian matrix. So the eigenvalue in the Hermitian operator omega are the so-called only possible observables, and the eigenvector of that omega actually form the basis of the state spaces. So the Hermitian operator omega basically equal to omega's conjugate transpose. Yeah. A dagger is not easy to write by hand, so using an etch is a bit easier. And the book actually then goes on to a lot of interesting concepts. Some of them are also going to mention that. There will be expected value of the observable. There's also the momentum. Yeah, once we have the quantum state transition, we actually can calculate the momentum of the transition. The book actually is actually the same principle we will think about with other systems. So with the quantum state momentum of the psi, the momentum is basically proportional to the minus that the previous state and divided by the how much change of that state. Remember, this is a discrete position on a line. And it turned out that proportional is actually defined by the so-called reduce Planck constant. White is there. I guess we have to go really read some theoretical physics to understand that. But that's just a definition of the moment. If we ignore that part, you will realize this is just the basic definition of moment. Yeah. So but the quantum part is just the coefficient is new to us. So with this, actually, there's a lot of a wealth of information will come from that. And so the book actually goes to talk about several Hermitian matrix property, which will be used to calculate the mean and the variance, mean and the most important mean and variance of the observables. So there's some very I think I probably don't have time to go over the actual content of this, but I'm going to quickly show the Python code so you can actually do some calculation on your own, I guess. So yes, so here are some examples show who instead of hand calculate, we can actually use Python to just verify this. So the Hermitian operator has some very interesting property. For example, the sum of two Hermitian matrices is also Hermitian. And we can actually just this is not a proof, this is just testing. We use two matrices to test this. And example, and then with that, we can also calculate the expected value of the observable. So when we when we observe something, what's the expected position? And with that, we can also calculate the variance. This is not a standard deviation, but similar concept. The book actually have a long explanation of that. So I think I will go over that next time, given how much stretch we have been going through just for the first part of content state. So let me stop here and just summarize what we have go through this. So today we go through the modulus and probability of each state. We show that a constant state multiplied by a complex number doesn't change the probability, which means we can use normalized state for most of the calculation. And we use the Bragg-Tate transition to show how quantum state transition from one state to the other using the transitional amplitude. Found out so-called transitional amplitude. I think that's. Let me look at all the important part. We also discuss the concept of superposition. So the important concept today we covered basic quantum state system, a particle at a discrete position on a line. A particle can be up and down. The complex number C0, C1, those are complex amplitude. And this a quantum system can be in discrete state. It's called superposition. We also showed how to estimate the transitional amplitude from the starting state to the end state. Okay, that's and briefly also went through the observable, which physical observable is the Hermitian operator. And I think we're going to I'll just stop here. Stop at the Hermitian operator.